Hello, this will be a demonstration of proposition 14 from book 2 of Euclid's Elements, which states to square a given rectilineal figure, that is, to make a square equal to a given rectilineal figure. All we are given is an arbitrary rectilineal figure A, like so. And given this rectilineal figure A, it is necessary to make a square equal to it, that is, to square the rectilineal figure A. First, we shall set out a right angle B. We can do this by a combination of simply setting out a straight line and drawing another straight line perpendicular to that straight line from one of its extremities. That would involve using 111. Now, in this angle B, we shall construct the rectangle BCDE and label it like so. And we can do this by proposition 145 in a given rectilineal angle to construct a parallelogram equal to a given rectilineal figure. Now, if BE be equal to ED, so if this side be equal to this side, well then the rectangle so constructed is necessarily a square, and we know it's equal to the rectilineal figure A, and so we can say that we're done with the proposition if the rectangle so constructed happens to be a square. Fortunately, this is not necessarily the case, and so if BE and ED be unequal, we shall say that BE is the greater of the two. Now, we shall produce BE to point F, like so, such that EF and ED are equal. This is a combination of postulate 2 to extend a finite straight line continuously in a straight line, and proposition 1.3, we've done this a bunch. Next, we shall bisect the straight line BF at point G. I'll say that the bisection point is there. It's proposition 1.10. Now, using the center G and the straight line GB or GF, doesn't matter if they're equal to each other, we can use either. We shall construct a semicircle, like so. And this is postulate 3, although it's only making half of the circle, but that doesn't change the fact that we're still using postulate 3. We shall construct the semicircle BHF, and we shall extend the straight line DE to the circumference, and this point I call H. H is somewhere around here. And the final step, we shall connect the straight line GH. Actually, not finally, because on EH we're going to make a square. Like so. We're going to call this square EHKL. This is not in the original proposition. This is something I'm adding, but I think it's a fine addition. Now, using proposition 2.5, that if a straight line be cut into equal and unequal segments, the rectangle contained, I lost it. The rectangle contained by the unequal segments plus the square on the straight line between the points of section will equal the square on the half. In this case, we shall deal with the whole straight line BF, so that the rectangle contained by BE and EF, which are the unequal segments of BF, plus the square on GE, which is the straight line between the points of section, the points of section being G and E, equals the square on the half. In this case, it'll be GF squared. We also know that GH and GF are equal. This is by definition 1.15 because they are both radii of the same circle, and so they have to be equal. And so we can say that GH is equal to GF. And so substituting GF here for GH, we can say that the rectangle contained by BE and EF plus the square on GE equals the square on GH. Now we can see that GH is the hypotenuse of a right-angled triangle. And so we can say that GH squared equals GE squared plus EH squared. This is proposition 147. And so by combination 1, we can say that the rectangle contained by BE and EF plus the square on GE equals GE squared plus EH squared. Subtracting equals from equals, common notion 3. We shall subtract GE squared on both sides, so that we can say that the rectangle B contained by BE and EF is equal to the square on EH. Now, because EF is equal to DE, we made them that way in the third step. By a property of magnitudes, we can swap out one containing side for an equal length and say that the rectangle contained by BE and ED, in this case, that's the rectangle BD, right? This rectangle is contained by BE and ED. So we can say the rectangle BD is equal to EH squared. We also know that that EH squared, we've made this squared. This is simply the square EK. And so we can say that the rectangle BD is equal to the square EK. Furthermore, we also know from the first step, we know that the rectangle BD is equal to the rectilineal figure A. We made it that way. And so common notion 1 tells us that the square on EH, namely the square EK, is equal to the rectilineal figure A. And, well, this square, which we have constructed, is equal to the given rectilineal figure. And so we can say we are done with the proposition that a square, namely the square EK, has been made equal to the rectilineal figure A, and that's QEF. I don't have anything to say about this proposition, and that's actually the final proposition of Book 2, and so I will move on to Book 3 and Proposition 3.1.